climate modelers start pushing these climate models further out into the future to get, again, these clues about the sensitivity of our Earth system. Looking towards later in the 21st century, we're currently projecting somewhere along the lines by 2100, 2.5 to 3 degrees Celsius. And that high tide on a very blue sky, sunny day is having water that's getting into communities. And I focused first on the Arctic because we're seeing really significant trends, melting ice in that area. We're seeing heat that's sometimes in extreme events buckling roads and bridges. Ice sheets, the Greenland ice sheet and the Antarctic ice sheet are showing signs of ice mass loss. First date for the first freeze is happening later and later in the seasons. This early warning then can allow communities to better prepare for extreme
Mhm.
weather. Changes in the Amazon, changes
Mhm.
in the ice sheets is
Yeah.
the real most classic tipping point. AI and machine learning tools are really good at working with lots of data, and they're really good at identifying patterns in the data. Science has constantly been trying to find ways to communicate this data, but it's difficult.
All right. Hello, everybody. Welcome to another episode of Science Talk. I'm your host, Dr. Mohammed Itafaq. In this episode, I'm grateful to my guest, who is a climate scientist and uses data driven methods to untangle climate change patterns from natural variability, providing clearer insights into climate risks. He also spends a lot of time thinking about how to make science more engaging through storytelling and visualization. He has a lot of following on social media, especially Blue Sky, after a lot of scientists migrated from X. When the word poorest guy took over, the platform, so a lot of people migrated to Blue Sky, including myself. So we're gonna be spending some time today talking about climate risks, climate impacts, future scenarios, extreme weather patterns, early warning predictions, and latest data science methods, how we use AI and machine learning to predict these projections and weather patterns. So I'm thrilled to be joined by Dr. Zeg. He works at Climate Central, and he can talk a little bit about his background other than his own interest and the work of Climate Central. Dr. Zeg, welcome to Science Talk.
Hi, well, thanks for having me.
Yes, so can you start us from the work Climate Central is doing and what you specifically doing there?
Sure. So Climate Central is a non-policy, non-advocacy nonprofit that really studies and tries to communicate climate change. So really what a lot of what we're doing is taking, global climate change through things like changes in temperature, changes in precipitation and other impacts and connect that to people, connect those impacts to communities to communicate and understand how climate change is impacting them today and into the future. And so, my role, I'm a climate scientist there, and much of what I do is trying to understand these ideas of climate risk, extreme weather events, which we'll be talking about, and how we can better predict and project those going forward into the future so that country or communities can better prepare and assess their own type of risk information for decision making.
Excellent. I actually did not know a long time ago. I recently learned that Climate Central is based in the US. I thought it's like a UK based or some other somewhere in Europe, but I didn't know it's non-profit. It's for profit. It's not a non-profit, which is interesting. But you guys are doing amazing and phenomenal work. At this time when we are hearing a lot of bad news, honestly, and not it's not like necessarily bad, but like it's real. That's the real picture. What we are seeing, a lot of reports coming out, which are scary, honestly, and more openly if we are like kind of see the data. You are the person who work with the data and analyze the data, visualize the data for people to understand, not only for general public but for overall for scientists. So a lot of work you do in Climate Central does is kind of climate risks. So I think let's start the conversation from here because climate change is all about risks, for societies, for individuals, for countries. What kind of risks are we talking about here?
Yeah, so just to clarify, Climate Central is a nonprofit.
It's a
And yeah,
nonprofit.
so we're
Okay. I thought you said a for-profit. Okay. It's a nonprofit.
sorry if
Okay.
I misspoke.
It's okay.
Nonprofit, and we focus a lot on the U.S. and climate risk, like you just mentioned, and we focus it on many different types of impacts. So one way is we look at communities across the US and we try to connect, as I said, these global scale phenomena to local scale phenomena. And a lot of that depends by season. So a lot of what we do at Climate Central is take a look at seasonally changing climate impacts. So for example, how is changes in when we get the first frost and freeze going to affect? We're in the time, the fall season
Yeah.
transitioning into winter. And often, this is when the time for northern states when we have our first freeze. When do we fall below freezing? And what we're seeing is just one example of climate risk is that that first date for the first freeze is happening later and later in the season. So instead of happening sometimes in October or the months of November for northern states, we're seeing that push into December. So this type of change in climate risk is having big impacts. So later freezes can impact health, it impacts pests and things like mosquitoes. It impacts even things like tourism and when changes in colors of fall leaves is going to happen across. So we take these sort of, physical thresholds, like when does the first day fall below 32 degrees Fahrenheit, and see how that corresponds to impacts that people are facing. So it's kind of one example what we do for climate risk. During the summer, of course, we spend a lot of time thinking about heat waves.
Mhm.
So how are changes in heat waves impacting communities through things like infrastructure? We're seeing heat that's sometimes in extreme events buckling roads and bridges because it's built beyond what the infrastructure was built for those extremes. It's also impacting people's health. So we're seeing many, during extreme heat waves, more and more people are going to the hospital due to things like heat exhaustion. So these are the types of ideas where we try to better understand the climate risk information, like a change in temperature, and understand then its connection to impacts. And we break that down at a local level.
And that includes individuals as well as a whole society and the community.
Yeah, very much so. So we really try to understand in your backyard, how you're seeing climate change. Maybe you're seeing plants. Maybe they're starting to bloom earlier and earlier in the winter because spring is happening sooner because of warming temps, but also to society, areas that we try to understand recently. We just re-released the $1 billion disaster data set where we tried to understand how weather and climate related extreme events correspond to financial risk across the United States. So, very much the work we do is understanding the local level, the national level, and the global level of climate risk and extremes.
And that risk and extreme data is coming from where?
Yeah, it's a good question. It's really coming from all over. Particularly, it's coming from a lot of it from federal data sources in the United States. So this is US and globally having very extensive data monitoring systems. So this is like real world observations. So examples of this is like collections of weather stations at different towns and cities across the region. This is also examples of like buoys in the ocean or ship observations, airplane observations, weather balloon observations. All of this very extensive network of like real-time data is collected by organizations like NOAA. And so they collect this data, process this data to produce these data sets. So we have them to understand historical weather. And this also helps to inform when we develop climate models, which are also done and many of our federal agencies to project that climate information out into the future. So all of this, this weather and climate data we have is built from a federal infrastructure of providing this free data sources that they spend time to quality control the data, to process the data and make it really easily accessible. And so we're incorporating all of this information into better understanding these climate risk components.
So that is a lot of data. Like it's a lot of data, right? There's a lot of different data points coming from different different sources, and your job is to look at data, feed to the computer systems. So, what kind of computers do you use, and what kind of softwares do you use to make sense? Because it's so much, and putting it to for a layman audience to understand this is what it means, or this is how the temperature has changed over the last 20 years, 10 years. It's a very complicated and it's too much work, isn't it?
Yeah, absolutely. Very good point. So many people say that climate science is one of the, most data intensive of the physical sciences because we're collecting
Mhm.
all these real observations and creating these model simulations to understand into the future. And there's a whole nother stream of data we collect that I don't think I even mentioned, which is coming from satellite
Mhm.
observations. We have so many satellite observations coming up and telling us different parts of the Earth climate system, things about the ocean, the land, the atmosphere. So we have all this satellite data that's coming in. So, there's no way when I look at this data that I can just look at the data and understand the patterns and trends that
Yeah.
we're observing in our climate system. So, we run statistical algorithms to evaluate this data. So sometimes this can be done on my, little laptop computer, but other times this requires really intensive, high performance computing systems, supercomputers, to really run these types of climate model simulations to understand, sometimes they project it into the past thousands of years. That's called paleoclimate. Sometimes they go, out 100 years into the future with future climate projections. So we sort of, much of what I do at least, is behind a computer, whether that's, working through a supercomputer at another location or through my laptop. And of course, then there's other climate scientists that are out in the field collecting real data using things like drone imagery for radars or collecting real observations, mooring data into the ocean that are going to places like the Greenland ice sheet, the Antarctic ice sheet, going out into the ocean. So there's so much data, and how do we make sense of it is just a growing question because every year we're getting more and more data sources, and that's a good thing. It gives us a better understanding of the climate system now and into the future, but it also, we have new questions of how do we sort through and analyze all this data and really make the best use of it.
Yeah, absolutely. And honestly, you're doing like a biggest service to the humanity, looking at like, hey, this is how it looks like, and this is how it's going to be in the future. So, be ready, like to the nations, to countries, and to people who make decisions and important decisions. And like kind of raised a very important point. Like we're talking about risks of climate change. But within that data, there are so many risks itself that if you forget to input some sort of data and it changes everything, right? So, for example, you collected all the different types of data, but you didn't put satellite data or the drone data coming from, and that might change the whole scenario. So, you have to be very vigilant on what you're feeding to the system and what kind of results you're going to get at the end. So it's like a very, like tedious kind of work that you cannot ignore anything before you put a final output out there for people to see this is what it looks like, because there are so many climate scientists and organizations and deniers who are looking at something into their data saying like, you didn't put this, you forgot this, so you don't want to be, approved inaccurate or like false or wrong, or give people a false projections or something, because that changes everything. Just like, oh, these scientists have been wrong and maybe they're wrong again. So it's like a very important work you're doing, absolutely, and it's very helpful for the scientific community to make decisions and projections. Now I want to talk a little bit about, these risks we are looking at from individual for the societies and other things. You have mentioned a lot of key terms and the data points. Like there's Arctic ice, there's ice sheet, there's a global sea ice, there are Earth system, there's a surface heat. A lot of things you have mentioned on your website. I'm gonna put that in the description for this, conversation so people can take a look at. It's a fascinating work you're doing. So does it like kind of differ based on the data you're receiving? For example, when you're dealing with temperatures, hot and cold, or you're dealing with, like the melting of ice sheet, or, the sea level rise, how do you kind of focus on what do we need to do, or how do we go or move forward? This is more important than anything else. How do you pick and choose or make things, more visualized based on that, instead of like just doing one thing and one thing only? You just look at the temperatures, but you're not doing that. You're doing almost everything.
Yeah, so I'm gonna revisit my past a little bit to help inform this answer. So originally, back in undergrad, I thought I was gonna go into weather forecasting. So I was very
Mhm.
much a meteorologist, got a meteorology degree, and I still love thinking about the weather, and I thought I was gonna go into doing some sort of, research around weather or, like I said, forecasting. And when we talk about the weather is something people talk about every single day. It's always changing. We're constantly, looking at the 7-day forecast and things like that. And eventually in college, I learned more about climate change and thought, what if I could better understand how changes in extreme weather due to climate change are going to happen into the future? And of course, that's kind of where my career path has gone. But I think this idea of how we talk about the weather and how we monitor the weather in like a daily, real-time way has informed my climate communication. So then for graduate school, I went into a program called Earth System Science. And what I
Mhm.
like to say is it's very much like a climate degree. So the idea of Earth System Science is that you have all these moving pieces. You have changes in the ice sheets, the ocean, the atmosphere, the land. They're all changing at the same time and they're all interacting with one another. So the idea is we need to think of all of these components as a whole to understand climate. And so these two components, this my interest in weather and this idea of taking all these pieces together is how I think about climate communication. So my goal is how do we take this climate data where sometimes we don't talk about it on a daily basis at all,
No, we
and
don't.
how do we monitor this really rapidly changing data and then communicate that to people to tell climate stories. So my go-to first kind of example when I started doing this was Arctic sea ice. So sea ice is something where we have daily satellite observations that tell us how much the extent of sea ice that's in the Arctic and Antarctic. And I focused first on the Arctic because we're seeing really significant trends, melting ice in that area. And I thought, okay, and instead of talking about sea ice, I don't know, a few times a year, maybe when it's at the maximum extent in the winter and minimum extent in the summer, what if we start talking about this more every single day? And I experimented with creating visualizations of this data because, again, we have these daily observations from the satellites. And how do we break this down, this complex, data-rich environment for storytelling to non-experts? And I started just posting on, at the time, Twitter and just posting a graph that I thought was a little less jargon for words and just a quick post saying, today it's a record low sea ice for the date. And I started quickly learning that there's a huge audience of people that are looking for this type of real-time climate information. They
Yeah.
want to be understanding where the data is coming from, how people are evaluating, and they don't want to hear about it, once a year. They want to hear about it, very frequently, more like we talk about the weather. And ever since then, I've just thought about, there's such a growing demand for this information. It's so important. It's changing so quickly in some areas like the Arctic. So I've just been slowly expanding kind of my portfolio of all of these different metrics of climate information because a lot of it we do have daily data. So we can talk about it, in real time as it's happening and building out sort of, these types of graphics for things like social media and my website and have continued to be surprised and amazed by how many people are looking for this type of information in the science behind it.
Absolutely, because the reason is that, historically, scientists just work and publish and move on, get the tenure and academic jobs. They never had kind of, privilege to interact with the public, with the media, with the social media. And now we are seeing more and more, which is amazing, that these scientists are going to the public through podcasts, through mainstream media, through social media, through a lot of other means, which is awesome for enhancing climate literacy and answer a lot of questions. And I think at the moment, you're right. Like, we don't talk about ice sheet or ice every day, other than the ice which we're gonna put in our drinks or ice which is on our streets. We don't talk about ice in the Arctic. So is it like is it the West Arctic or Southeast North? Because there is also a difference where somewhere is melting more than the other. And is that like also just for the clarification, my understanding and for the audience, most of the data which is coming from the Arctic is through satellites, or there are also people on the ground who are collecting data through other means. And also, some people would argue that's harmful for the environment. And how do scientists do that?
So, yes. So, one advantage I think to, like I said, communicating this climate information is real time is we can help answer some of these questions that might be really confusing. Like,
Yes.
when we talk about polar sea ice, where is all this sea ice changing? What's land ice? What's sea ice? How does that affect our sea level rise? So,
Exactly.
again, an advantage of all of this communication in real time has been that I can help educate on some of these topics or help answer questions that people might not get chances to ask. So, for the Arctic, that's the North Pole region. So basically, that's an Arctic is an ocean that is sea ice covered during the winter time and is surrounded by continents. So on one side is like North America, the other side is Europe and Asia. And then on the other side of the world is the South Pole, and that's the Antarctic. So that's where we have the Antarctic ice sheet in the middle, surrounded by the Southern Ocean. So sea ice grows around the Antarctic ice sheet. As far as, changes in these regions, there so far have been fairly different trends. There's a variety of complex reasons why. So Arctic sea ice has been one that's very clearly been melting over the long term. So we're seeing a rapid loss of Arctic sea ice when we look at the last, 4 decades or so of satellite observations. The Antarctic sea ice, the trend has been a little bit less clear, although recently we're starting to see signs that that ice might be melting too. And that's sea ice. So that's frozen ocean water that does not contribute to sea level rise and our rising oceans along coastal communities. What contributes to that is coming from land ice. So you can think of
Mhm.
land ice being the Greenland ice sheet that's located towards the Arctic, and then the Antarctic ice sheet, again, located in the Antarctic near the South Pole. So that's ice that's basically sitting on like a continent. So when that ice melts, that water now goes into the ocean and that contributes to our rising seas that,
Mhm.
cause the sea level rise and flooding concerns. And so both ice sheets, the Greenland ice sheet and the Antarctic ice sheet, are showing signs of ice mass loss. So far, that's been larger in Greenland, but that could change depending on some projections out into the future. So yes, so that's been a quick
Yeah.
intro to the polar sciences, but as you can see, there's lots of moving pieces, and how do we take account of all of this? And so where a lot of this data we're getting from is satellites. So I would say on a daily basis, like a picture snapshot of both polar regions is coming from satellite data, but there's lots of other data sources as well. So we do have people that do go to the Arctic and Antarctic to collect actual in-person observations. So there are science bases in Antarctica that, have people living there several months out of the year where they can collect very important data on the ice sheet. There are also field cruises where they take icebreakers into both the Arctic and Antarctic to collect data about the sea ice. They drill into the sea ice to collect a really small ice core to understand, how thick or thin the ice might
Yeah.
be. Collect things like how much snow is there, the measure the snow depth. So there's so much of this rich data coming from multiple different sources that are really important for understanding change in these regions, especially where it's happening really quickly.
So the Iceland ice sheet, I think, recently also made to the headline saying that Iceland is sounding alarm that it's a very, a national security risk for them, right? And also Antarctic ice sheet that is melting faster than ever, and we're seeing it's becoming more thin, right? And that is happening because the surface temperature is increasing, and that is causing the melting, right? If I understand it correctly, or there is more into that. And also, with that, if you can talk a little bit, if it continues melting, which regions are more vulnerable to the sea level rise than others? Because definitely there are certain parts, of course, coastal lines and cities which are near to the oceans and seas are more vulnerable, while like in terms of regions and the communities who are at bigger risk if we think about or the impact of those melting ice sheets.
Yeah, absolutely. So contributing to ice sheet loss
Mhm.
is several different pieces. As always, the picture is complex. So in addition to warming atmosphere temperatures, air temperatures, it's also that the ocean is warming. So some
Mhm.
of that really warm ocean water can actually get underneath parts of the Greenland ice
Mhm.
sheet and Antarctic ice sheet, particularly around the edges. So that can actually contribute melting from the bottom of the
Mhm.
ice sheet, bottom melt. So sometimes the melting can come from the top of the ice sheet, but also the bottom. So there's multiple factors that contribute to
Mhm.
why we're seeing this land ice melt over time. And a lot of researchers, what they do for areas like, well, both ice sheets, is that they focus in on specific glaciers that are part
Mhm.
of the ice sheet, individual glaciers, to try to understand changes in that specific glacier on the ice sheet and how that is, either it's stable or unstable, and what are the projections of that forward into the future. So a lot of the research focuses on very specific regions.
Mhm.
And then, as part of the scientific process, we take a look at these assessment reports of all of the regions together to make those really big global projections of sea level rise. And so if we look, going forward into the future at these sea level rise projections, we can see that, there are many coastal communities all around the world at risk. But there's different amounts of risk
Yeah.
depending on
Mhm.
location. Some areas are just built in more vulnerable regions to flooding. So, but we're already, I talk about projections into the future of sea level rise, but we're already seeing impacts of sea level rise today. And
Mhm.
so some examples that I like to point to of that are really clear examples that sometimes go by a nickname called sunny day floods. So
Mhm.
that means that you will have flooding in coastal communities, not necessarily because there's a big storm, or hurricane nearby, but it's just because you have a high tide. And this
Mhm.
high tide is now higher, the water level is higher than it would have been without sea level rise.
Mhm.
So one area that's really been observing this is across the Miami. So Miami is starting to have these very high tides that are higher than they would have been otherwise without climate change. And that high tide on a very blue sky sunny day is having water that's getting into communities. So they're
Mhm.
having to invest millions of dollars to build these pumps for these days where there's just no storm, but we're seeing rising seas that are getting into infrastructure, into roads. And so, this type of thing will continue going forward into the future. There's even been some research to suggest that sometimes these smaller floods, when you add them all together,
Yeah.
will end up being more costly than, just having one big hurricane come. So certainly the changes in the ice in the very far remote polar regions have real world impacts in where people live.
So it's a Greenland ice sheet, not the Iceland ice sheet. So I just want to make that clear, right? So,
Yes, Greenland
okay.
ice sheet and Antarctic ice sheet.
Okay, perfect. So generally, you collect the data, and on the other hand, we are seeing reports that we are burning so much fossil fuel, and the temperature is increasing every year. And if we see in totality, we already reached 1.5 degrees Celsius, which IPCC projected by 2040, and there are a lot of scientists say like 2024 was the first year. Now we are seeing 1.5, 1.6, and we might hit 2.6 or 2.5 by 2040, and then 3 degree by 2050. Now, when you look at these, reports which are coming out from World Meteorological Organization and many other organizations which are projecting how the trajectory is going to look like in terms of the temperature increase in your estimates, in your projections, in your data, what do you see the worst case scenario or the least worst scenario if we hit, let's say, hypothetically, at which I mean, it's not even hypothetically, that's the wrong word to use, maybe. It's looking at more realistic that we are going to hit 2050, like 3 degree by 2050. If it happens, what would happen to the sea level and what would happen to these ice sheets? And what
Yeah,
impacts would it have on these coastlines and the communities?
Yeah, sure. Just to clarify,
Mhm.
so there's many different ways of looking at global temperature as far
Mhm.
as the trends and projecting that into the future. And when we actually take a look at a lot of the models that go into assessment reports like the IPCC, they're actually doing a very consistent job with projecting those temperature trends. So right now, looking towards later in the 21st century, we're currently projecting somewhere along the lines by 2100,
Mhm.
2.5 to 3 degrees Celsius. So very much our climate models are really helpful tools providing us insights to these things like climate risk. And so one way we take a look at different levels of the risks, sort of worst case, best case
Yeah.
scenarios, on one hand is, looking at different emission scenarios going forward into the future. So how much greenhouse gases are going to change? And there's many, left open questions about, trying to predict human behavior and
Mhm.
technology into the future. But another way we do it is a technical term, but I'll try to explain it, is we run something called a large ensemble. So what that means is we take a climate model and we run that same climate model simulation multiple different times, sometimes 100 times. And what we try to do is we try to simulate the chaos of weather. So, as we've discussed on here, there's changes every day from weather changes. There's also changes that from year to year just due to weather chaos in our atmosphere. So we try to simulate some of those extreme events and that weather uncertainty, incorporate that into future climate change projections. So we run these climate models to incorporate not only just those greenhouse gas differences, but also this just weather differences to try to understand the range of possible extreme weather events. So it's very hard to summarize, what those projections look like on a call like this. But I encourage, the viewers to check out some of these recent assessment reports that provide these uncertainty ranges to talk about, for example, what are best and worst case scenarios for changes in heavy rainfall, extreme precipitation that has big impacts for communities and infrastructure. So this is kind of, at least from my perspective as a person who works with climate models and helps to run them, that's how we try to provide these assessments going forward into the future.
So do you think that it is time, it's 2025, do you think it's time for scientific community or for these organizations to go beyond 2100, or we still should be looking at, because when I talk with a few scientists, they say like that's itself a problem, but you don't, of course, you don't have to agree with that or disagree with that, but like, do you see that we should be projecting, scenarios beyond 2100?
So it's a great question. It's something that I have thought about and has come up in a lot of conversations in the past. And so it's difficult for a couple different reasons. One, like I said, we try to predict, as part of these future scenarios, we try to understand changes in greenhouse gases, but trying to predict that beyond 2100 happens, considering things economic, societal, political, futures that'll inform how greenhouse gases evolve, of course, is, extremely difficult to do that far into the future. Another thing that is just to have the resources to actually run the climate model simulations that far into the future can be expensive, both computationally, the amount of scientific computing, but also to get the resources to do at these institutes. But I think there's a lot of good reason that we should be running climate model simulations more and more as they become more advanced further out into the future to understand these Earth system changes, understand how our oceans circulation, how changes in the ocean will evolve over time. How will the ice sheet evolve over time? And we can get better clues if we extend these simulations well out into the future. So they can't provide any exact specific answers, but they can tell us a lot of clues about the sensitivity of our Earth system to things like climate change. So I think we're going to see more and more in the coming years that climate modelers start pushing these climate models further out into the future, to get, again, these clues about the sensitivity of our Earth system. But just a lot of open scientific questions, but people are thinking about that, which is very encouraging.
Yeah. So, it doesn't seem, but like, of course, you're very passionate about the work you do, and you look at the data, which is real-time data coming from many sources. And when you look at the data and the picture is not looking good, you see like, man, we're doomed. It's too much. It's like too dangerous. And it's like the path we are taking is leading us toward devastation. How do you keep up with that as a hopeful person, or like, are you more of a depressed or pessimistic person, or like, kind of, where do you see that, oh yeah, we have this, but like, I think we can do this? So where is that, enthusiasm, or keep going for this kind of work? You keep going, what motivates you, what keep you going? Because
Yeah,
if I would be seeing that data, I would already be like, man, that's too much, I'm done.
I get this question a lot, partially because I think a lot and communicate a lot about the Arctic, which is
Yeah.
really changing fast. And so for me, what keeps me motivated is goes back to when I originally starting actively communicating this science. I am just constantly surprised when I post a graphic on social media that I think is pretty technical.
Mhm.
Science information, pretty complex, but there's so many people, non-scientists, that are interested in learning more about this information. And I get many people each week that message me sharing how they've used
Mhm.
my graphic in ways that I couldn't have even imagined when I started it years
Wow.
ago. Using it at museum exhibits, they've used it in art galleries, they've used it in elementary school classrooms to understand, data. So to me, it's just seeing that there are so many people passionate and wanting to just learn more, have a more direct line of communication with the scientists doing the work. And I think that really keeps me motivated. And, related to this point is when I talk to, I mean, I think I'm fairly still early career, but when I talk to more early career scientists and hear about the new ideas, the new methods, the new technologies to start better understanding climate change, climate impacts, climate risk, it gets me so excited to think about all the creative ways that we can better understand through better models, through better statistics, through better data to warn communities in advance of some of these hazards.
Absolutely, yeah. I'm by myself as an early career. It's been 3 years. It's a fourth year. I'm assistant professor. So I exchange a lot of ideas with new folks, and it's exciting. And yeah, so what's some of the technologies which are really helpful, with early warning systems or predictions or like the type of analysis or you do? What kind of technologies are super helpful to you? Because AI is everywhere. It's a hype right now. It's a buzzword. It's everywhere. So in especially climate models and visualizing this data, how much help do you take from artificial intelligence or machine learning or whatever other technologies you're using?
Yeah, so for AI, I use AI, and most scientists use AI in a very different way than people think about it now, hearing about it on the evening news, where they think about, large language models
Hmm.
that they type something in and get a response. So what we often are using is these AI machine learning algorithms that are very much at its simplest, explanation. It's just fancy statistics. It's very different, like I said, than the ones you're hearing about on the evening news. And so a lot of these tools, to throw a few words out there, or we're using machine learning methods like a neural network.
Hmm.
Neural networks have been around for decades. It's not that new. There's examples even in weather and climate research going back many decades that have used things like neural networks. So we incorporate some of these fancy statistics to better understand patterns in our data. Earlier, we talked about, you asked a question about how do I sort through all of these billions of numbers. And so these types of AI and machine learning tools are really good at working with lots of data, and they're really good at identifying patterns in the data. So an advantage for something like a neural network is it's able to find the patterns in the data, let's say changes in temperature, and they're also able to incorporate some nonlinear relationships and connections in the data that other statistical methods might not be able to distinguish. So it can be really valuable for understanding where changes in climate patterns and trends have emerged. So a lot of my research has incorporated machine learning algorithms like neural networks with climate model data and real world observations, and they've incorporated them all together to tell us where has climate change emerged in different parts of the world. So that's been one tool. Another tool relates it to climate prediction side of things, where, like I said, these machine learning algorithms are really good at finding patterns in the data. And so we're constantly trying to improve prediction skill for going out, let's say, a season to a year to a decade into the future with better and better skill. So one thought is, can we use some of these new statistics or different ways of these algorithms with some of the data to improve that prediction skill? So this is called a forecast of opportunity. So basically, it's what it sounds is that it tries to identify some sort of signal, let's say it's a pattern of ocean heat, that can lead us to make a better prediction. Let's say how bad heat waves might be next summer. And this early warning then can allow communities to better prepare for extreme
Mhm.
weather. So that's the ultimate goal. There's a lot of research to be done. This idea of combining these types of machine learning tools with the newest high resolution climate data is still very much left to explore. And there's countless scientists working on this topic, but it's all leading towards better predictions to better inform about impacts, and so that more and more early warning can be provided.
So, August, at least these, neural networks and machine learning is very helpful in terms of these projections and predictions and analysis of these complicated data sets, which is great, to know that technology is helping us, if not, leading us to collapse of civilization or other things. So, another like a more of a social scientific question is, do you we now, fortunately, due to a lot of data and a lot of analysis, we know a lot about these, changing patterns and ice sheets and temperatures and everything. But scientists were doing this work for decades. And this work was never made this much accessible to the public, and conversation we never had at a large as a society about these impacts and devastations we're gonna look and see in the future. Do you think scientists, not to use the word like have failed to like kind of communicate these things with the society, or like what should have we done better in terms of communicating these risks and impacts with the general public 10, 15, 20 years ago, what we are doing now?
Well, honestly, I think climate scientists have been doing a good job of communicating this information, but it's tough.
Mhm.
And I think, how climate is communicated also has really evolved just with
Mhm.
society.
Yeah,
Social media is such a huge player
yeah.
in constantly evolving too. Different social media platforms are changing in popularity as well. And
Mhm.
so I think it's just different types of communication that are ongoing. But I
Mhm.
think reflecting on the past, we can see wonderful examples at the time of trying to communicate the urgency of the data. And we can look at the earliest climate model simulations of the future from, over 50 years ago and see that they actually did quite a good job at identifying what parts of the world are going to see the largest climate change, temperature changes going forward into the future. So I think there's many examples of science has constantly been trying to find ways to communicate this data, but it's difficult, and
Yeah.
so we're constantly evolving to figure out what ways are most effective. When people they ask me about my own communication strategies, I like to say that to me, in my view, I want to be very clear. I'm not a social scientist or an
Mhm.
expert communicator. But for me, I found that there is no perfect way to communicate climate change information. And I always encourage people to follow their passions. So for me, my passion is sticking with the data and finding ways to break down the complexity of the data and make it more visually appearing to tell stories. For other of my colleagues, working on communication, they tell human-driven stories about impacts to their communities in more imagery rather than data. So I find that there's many different ways to
Yeah.
communicate this information, and I encourage people to try different ones to really align with their passions.
Absolutely. And you've been very successful, honestly, like, and you're excellent communicator, I would say, through your website, through social media, and even through talking. Do you see a lot of conversations these days happening about tipping points? What is the tipping point for these ice sheets? What temperature would be, and then we will see like this is a tipping point for, for the global ice sheet or like, Antarctic or Greenland.
Yeah, admittedly, this is not my area of expertise as far as my research. In real short, what a tipping point is it means an irreversible
Yeah.
change.
Hmm.
And so scientists are trying to understand whether there are tipping points in the climate system that are at risk. So they look at things like changes in the Amazon, changes
Hmm.
in the ice sheets is
Yeah.
the real most classic tipping point.
Hmm.
So I think that there's a lot of research actively being done. Sometimes it can be really challenging to communicate the nuances of what a tipping point is and what that means. What are the uncertainties? Sometimes I find that the uncertainty isn't communicated as clearly, but it's difficult. So I would encourage people, if they're interested in this topic, there are lots of scientists who are experts on tipping points, and I encourage to follow some of the assessment reports that come out from the climate community because they really take into account an umbrella of the research rather than just one paper finding a finding. They really incorporate all of the scientific research, sometimes that might not get picked up by the media. And so that those can be really valuable tools for interpreting what are risks related to tipping points.
Absolutely. So, last question before you go. So, what is something still missing from these conversations, and we should be spending more time talking about, risks and impacts and ice sheets and global temperatures and, melting ice related to climate change?
I think it really relates to something we've been talking the entire time, which is data. I think there is still a lot of research to be done to speak about real world observational data. We often want to talk about the newest AI method or the newest fancy climate model simulation way out into the future. But there's a lot of research to just better understand, collect more data here on our Earth, collect more buoy observations to tell us about our changing oceans or build more weather stations to better assess the network of weather stations to talk about data across many different continents. So I think I would always emphasize that there's still a lot of scientific questions that revolve around better improving our real world observational data, and by better improving that network, that can tell us a lot of information about how our climate is changing and what it might look like going forward into the future.
And that would be great for, adaptation and mitigation in the future and in terms of policy frameworks and how we respond to these changes if we look at data more closely. So thank you so much with that. Appreciate that so much coming on the show.